I'm absolutely driven to succeed at this. The most motivating thing that somebody can tell me is that it can't be done.
While working on her PhD in chemical engineering, Dr. Nancy Mathis developed a sensor that measures various properties of a material using heat transfer and effusivity. Today, Mathis instruments are successfully marketed worldwide. Dr. Nancy Mathis, recipient of the 2003 Principal Award.
Non-destructive thermal effusivity sensors are something that was invented during my PhD research in chemical engineering at the University of New Brunswick in Fredericton. And these sensors change the way thermal properties can be measured in a variety of materials. It's non-destructive, it's rapid, and this takes the place of other techniques which took hours to measure how a material transferred heat.
Non-destructive thermal effusivity sensors can be used to detect irregularities in a variety of materials where consistency is required.
Effusivity is the ability of a material to transfer heat, and every material transfers heat in a different way. The experiment that I do with people that you can do sitting in your seats is to put your hand on a piece of material like paper or foam, and put your other hand on a piece of material that's metallic, maybe even silverware. Put your hand on both of those objects, and one of them will feel colder. The metal feels colder to your touch, but both of them are at room temperature. The reason the metal feels colder to your touch is that the heat transfers from your hand into the metal more rapidly. That's because it has a higher effusivity. And just like your hand can differentiate between paper and metal, our sensors can differentiate between computer chips without a crack or with a crack. Our equipment not only tests thermal effusivity, it also tests thermal conductivity, and that's what's best known by the market. Thermal conductivity testing before used to be conducted on samples that were 1 foot square and 1 inch thick. And they were put into an instrument similar to a VCR, and you had to wait for roughly an hour to get the measurement. With our sensors, they operate more like a stethoscope. A sample is put in contact with our sensor, and in roughly 5 seconds, you have the answer for the thermal conductivity or the thermal effusivity. We have heating elements that supply the heat source into the material being tested, and also monitor the temperature that results from that. So this is the heart and soul. It sits inside of the overall sensor, and this is what the customer interacts with. This sensor is placed on top of the materials that are under evaluation, supplies the heat, and it detects the heat flow. And from that, in about 5 seconds, you have a measurement of the thermal conductivity and thermal effusivity, worlds away from the half hour to hour that it used to take before. One of the best applications for our technology right now is in the blending of powders used to manufacture pharmaceutical products. As powders blend, it's important for them to be uniform in nature before they're used to make tablets. Nicely, the different powders have different effusivity properties, and our sensors are placed in different locations on the side walls of a blender. When the material feels the same to our sensors, the powder is the same, and it's time to go make tablets that'll be uniform. So in a blender, the material blends, it tumbles, and all of those ingredients mix together. With pharmaceutical products, you don't want to have all of your active ingredient in one tablet. We have our sensors actually retrofitted into the side wall of the blender. When all 8 of our sensors read the same value of effusivity, it's because the material that they're in contact with is the same. That means the tablets that come from that blender are going to be the same in medicinal content. There are about 60,000 of pharmaceutical blenders in operation today. Our device sells for $60,000 US. With that type of market opportunity and the replacement business on the sensors in use, the opportunity for us totals more than $2 billion. So it's an application to chase.
Mathis instruments can be used to detect hairline cracks, separation of liquids, contamination in petroleum products, and blend uniformity in powders. As more industries learn about Mathis instruments, new markets are born because consistency is at the heart of quality control.
There's no limit to where this effusivity sensing can take us because every material transfers heat differently. If you want materials to be the same or you want them to be different, we measure consistency. So one of the elements for me that's important with winning this award is it gives my staff, especially my senior staff, something to share with their families that says, see, this is important. I'm doing important work because I'm working together with Nancy to make this a reality. We all have to stop being our own worst critics. So many times you hear comments of, well, if it was any good, it would be done someplace else. Not so. There are amazing innovations happening here in Canada, and this award credits those.